The session coming up next, Pixel Perfect Timing Attacks by Paul Stone. I just ask that you hold your questions to the end of the session. We'll make sure there's time at the end. There's a mic down this row for you to ask your question if you're from the back, or if you yell out from the front, Paul will be so kind as to repeat your question and then answer it. I would also ask that on your way out, if you just scan your badge, they'll email you the evaluation form, and the feedback's very appreciated by both Black Hat and the speakers. So thank you guys for doing that. And without further ado, I'll pass the floor.
Okay, thank you guys for coming. I'm Paul Stone, and I'm from Context Information Security. We're based in the UK, and I'm going to talk today about timing attacks. So, timing attacks, one way of looking at them is as a black box with some secret inside that we want to find out. And we can use a timing attack to try and get at those secrets. So we put some input into this black box, and we get an output, and we time how long that output takes to come through the box. And then we give another input into the box and get another output, and we time it again. And actually the output from the box isn't necessarily all that important. What we're interested in is the times. And if we can correlate the inputs we put into the box with the times, then perhaps we can find out something interesting about what's going on inside that box. And usually we have to give quite a few different inputs to figure out what we're trying to get at. So I'm talking about browser timing attacks, and what kind of black boxes are there in web browsers? So one of the main black boxes is also the foundation of browser security, and that's the same origin policy. So basically, the same origin policy says that one website shouldn't be able to read or modify any data from another website. So the online banking website you're logged into shouldn't be able to be affected by any other website that you have open at the same time. So even though there's this restriction with the same origin policy, websites can still make requests to other websites, and there's various different ways of doing that. One way is with an image. So one website can load an image from another website, and it will display on that site, but it can't it can't actually see the content of the image. And there's other things as well. You can one website can load a script from another website, and things like XML HTTP requests can make requests, but by default the website can't read the results back. So yeah, those are kind of black boxes from the point of view of a website. They can put some data in, but they can't get any data out. So the particular black boxes that I'm interested in today are these two things. One is link colors. So when you have links on a web page pointing to other websites, usually they're different colors depending on whether you visited those or not. So that's kind of some private information. And the second thing is iframes. So by default, one website can load another website inside a frame, and although it can do that, it can't actually get inside the iframe. It can't see what's inside there, again, because of the same origin policy. So here's a distant example of that. So here's a website. Any website can do this. It can put a bunch of links on the web page, and it can frame, in this case, just your Amazon account page if you're logged in. And there's private data that you can see there. So you can see that as a person using your browser, but the web page can't see that private information. So it can't tell if those links are visited, and although it can load in the Amazon page, you can't see what's inside there. So today I'm going to be talking about doing browser history sniffing with timing attacks. I'm going to look at how you can read pixels from iframes using timing attacks, and I'm going to use relatively new browser features, HTML5 and related things, to do that. And I've got some fun demos as well. So before I talk about all the new fun stuff, I'm going to show you an example of a timing attack that's been around for forever, pretty much, just as an example of how timing attacks can work. So this is called page request timing, and it's about timing network requests. So let's say that I want to know if you're logged into Gmail. I get you to visit my website, and I run some JavaScript to try and figure out if you're logged in. So here's how the JavaScript will work. So first of all, it gets the current time, the timestamp, Date.now will give you the current time in milliseconds. And then we use an image. We use an image request. So in browsers or in JavaScript, the simplest way to make a network request is with an image. Now, you don't actually have to request an image from the network. You can request any URL that you want to, basically. So in this case, we're going to request the Gmail website. So as soon as we set image.source, the browser will go off and start fetching that URL. And of course, it's not actually an image. And eventually, the browser will realize that and go, hang on, that's not an image. And it will call my on-error callback. So it'll call this function, and then I can get the timestamp again and figure out how long that network request took. So in terms of the black box, the image request is our black box. And the URL that we give is our input. The on-error callback is the output of the black box. And the thing that we're interested in is the time it takes. So we use date.now to time how long that process takes. So what happens if you're not logged into Gmail? Well, when the page requests the Gmail site, Gmail will redirect to the Google Accounts page, and the browser will, even though you just made one request, it will keep following the redirects until it gets a result. So in this case, it will redirect to the login page. And if you are logged into Gmail, then first of all, you'll be redirected to the accounts page, but because you're logged in, that will redirect you back to Gmail, and then it will do a couple more redirects. So because there are more redirects to follow in the second case, that will take longer. So in the first case, it's about 400 milliseconds, in the second case, about 700. So we can test this a few times. So we send a bunch of requests when we're logged in and when we're not logged in, and we can plot those in the graph and see that, yeah, on average, if you're logged in, then the request will take longer. So let's say that I do this. I make my web page and I do this request, and I get a result of 500 milliseconds. So are you logged into Gmail or not? Well, this brings us to some of the difficulties of doing timing attacks. And there are quite a few problems with doing timing attacks in the wild and making them reliable. So one is network latency and jitter. Each time you make a request, it will take different amounts of time, especially if you're doing things over the network. And also, I don't necessarily know how long that response will take from your computer. So I might have tested it on my computer, and it takes a certain amount of time, but you may be somewhere else in the world, you may be closer or further away from Google servers, you may have a faster or slower computer. And also things running on your own computer can disrupt the timing. So if you're encoding a video or got lots of other browser tabs open, it can affect the timings. So these are problems with doing a reliable timing attack, but they can be overcome. So to overcome the jitter, we can take multiple measurements and take an average. If I don't know how long a request to Google might take from your computer, well, we can calibrate against a server that we know will take a certain amount of time. So we might make a request to a Google server that will always return the same response. And if there are things, other network requests running or other processes, the JavaScript on the web page can wait maybe just a few seconds until the computer's idle, and it can get more reliable measurements. Okay, so that was a timing attack that's been possible since forever. So just as an example. So now I'm gonna look at how we can sniff browser history with timing attacks. So a long time ago, about 3 years ago, it was possible for every web browser could do this. It could sniff your browser history. It could find out what websites you visited. And it was very, very simple to do. So here's the code it would need to do it. First of all, it would set some styles on links. So this basically says all links are blue in color unless you have visited them, in which case they're red. And then the site can create a link on the web page, say to PayPal. And then this little bit of JavaScript basically gets a reference to the link and asks the browser what color the link is. Very straightforward. And if it's red, then it's visited. If it's blue, it's not visited. And it was possible to... Sorry? Yeah, it's possible you can make this entirely invisible to the user, so you wouldn't necessarily see that PayPal link on the screen. So it's possible to do this for thousands and thousands and thousands of links in a very short space of time, and you could build up a profile of the user, which is obviously a big privacy problem. So someone actually did a study in 2010, and they looked at the top 50,000 most popular sites and found that a whole bunch of them were actually using this sniffing attack to find out what sites people have visited and send those results back to a server. So there were some adult sites that were doing this, and there was at least one ad network that was doing this and sending out this JavaScript to lots of different websites to find this stuff out. So and there was quite a big fuss about it. This has gone from being a kind of a fun theoretical attack to something that was actually going on in the wild, and there were lawsuits and things like that. So it was quite the serious stuff. But the history sniffing attack has now been fixed. So Mozilla came up with a solution for it. It wasn't simple. So in 2010, they proposed a fix. This had been possible for about 10 years in every single web browser. This attack had been there. But now all browsers have implemented this fix, and there are lots of restrictions on what you can do with links. So you can only change the color of the link. You can't change the background image or the size if it's visited. And the browser will actually lie to you now. If you ask the browser what color of link it is, it'll always tell you that it's not visited, even though it is. So I quite like this history sniffing attack. I first came across it back before I was in this industry, and I thought it was quite fun. So I decided to bring it back with a timing attack. So how can we do that? So requestAnimation frame is part of HTML5. Okay, technically it's not part of HTML5, but there's HTML5 in the title of my talk, so let's pretend it is. Lots of other people do as well. So what is requestAnimation frame? Basically, it lets web pages do nice, smooth animations. So if you've done a bit of JavaScript before, you might have heard of set timeout. So set timeout, you give it a callback function and a time delay, and it'll call back after, say, 10 milliseconds or 50 milliseconds. And in the past, you could use set timeout to do animations, but requestAnimation frame is synced to the refresh rate of your monitor. So the idea is you pass a function to requestAnimation frame, and it will call back your function just before the browser is about to draw the next frame. So the idea is it will give you nice, smooth animations, roughly 60 times a second. It will update the screen on most monitors, about every 16 milliseconds. So most of the time you can get a nice, smooth animation. But if things are taking a bit too long, if the JavaScript is a bit too complex, or there's too many complex graphics on the web page, things will slow down, and the interval between the frames that are painted will slow down too. So requestAnimation frame is interesting because we can use it to measure the frame rate of the entire web page, not just our animations that we're doing, but everything that's going on our web page. So when I saw this new function appear in browsers, I thought, maybe we can do something interesting with this to do with timing attacks. So I'm going to show you a quick video now, and this is a video of. Let me try and find it. So this is a video of me in Internet Explorer 10, typing in the search result to Google and going to Wikipedia. Absolutely nothing interesting there, you might think. But I'm just going to go back and kind of step through that in slow motion. And we're going to see something slightly interesting. Right, so I'm going to step through now. Just as the search results are about to appear, we're going to see something interesting. Well, fairly interesting. Right. So the search results have appeared there. And just keep your eye on this link to Wikipedia here. So at the moment, this link is blue. And as we step a few frames forward, it's just turned purple. It's a little bit subtle there. The color's not too different, but hopefully you spotted that. Let's back it up again. Okay, so blue, frame, purple. So, and the same thing happens when the Wikipedia page loads up as well. These links are blue, and I think they turn purple. Yeah, there. So you might be thinking, why is that interesting? Well, I'll tell you. So what's happened there? So this, I recorded that in Internet Explorer, and let's break it down frame by frame. So first of all, the page begins to load, and we have nothing on the web page in our first frame. And then in the HTML or possibly JavaScript, inserts a link onto a web page. Let's say a link to Google. Now, when the browser knows it needs to render this link, it does a request into its history database to find out if that link is visited. But it's an asynchronous request. It doesn't wait for that response to come back. It just goes ahead and draws the link. And it draws it as unvisited because it doesn't know yet if it is visited. So this request takes a few frames to come back, and then that database query completes, and it finds out that actually google.com is visited, so it repaints the link. So we can think of this as maybe 5 frames, but actually the browser only had to draw something on the screen in 2 of those frames. So it drew it first unvisited, and then when it found out it was visited, it redrew it. So what if the link wasn't visited? Let's go step back, and okay, so the database query completes, and we find out the link's not visited. Well, in that case, nothing happens. The browser doesn't need to repaint the link, and we only have 1 frame where something is actually painted on the screen. So I thought, well, if we can detect those repaints, then perhaps we can find out if that link is visited. But the problem is that requestAnimation frame doesn't tell us about repaints. It only tells us the time between frames. But perhaps if we could slow down the frames where that painting occurs, then we could detect the repaint. So how can we slow things down? Well, one way, it's pretty straightforward, is using something called text shadow, which is part of CSS. So we can take a nice, boring, normal-looking link and apply a nice, funky text shadow to it. So in this case, you can specify an offset, a blur radius, and a color. And you can actually have more than 1 shadow on a link. So in that case there, we've got 2 shadows. And this slows things down a lot. And also, if rather than just having 1 link, we can have lots and lots of links, then all of those links would have to be repainted if the browser finds out it's visited. So hopefully this will slow things down a bit. So here's how it might work. So in our normal case, with a nice quick link to draw, every frame, we're going at 60 frames per second, full throttle. Every frame takes an equal amount of time to draw. But if we apply the text shadow and have lots and lots of links, then perhaps those frames where the repainting occurs will be slower, and we can detect that happening with requestAnimation frame. So let's go back to the black box again. So this time, the entire page rendering pipeline is our black box, and everything we draw on the screen is our input. But in this case, specifically, the link and the URL of the link is our input. And the requestAnimation frame callback is our output. And of course, the delay between the frames is the timing data that we can hopefully use to figure out if that link is visited. So here's how this attack might work. So we have a whole bunch of URLs. We want to find out if they're visited. And for each URL, we make a whole bunch of link elements on the page with nice text shadow to make it nice and slow. And as soon as we put those links on the page, we use requestAnimation frame to time the next few frames, how long they take to draw. And in theory, if we have 1 slow frame, then we know the URL isn't visited because only 1 repaint occurred when the links were originally drawn. And if there are 2 slow frames, then we know the URL is visited because we've had a second repaint. So let me show you a quick demo of that. So this is in Internet Explorer 10. It works in Internet Explorer 11 as well. Okay. So what's going on here? So just so you know, this is what I've been using to experiment with this technique, but none of this needs to be visible on the web page, right? So all of this could be completely hidden. It could be happening inside an advert iframe and not be visible to the user at all. But this is just so we can see what's going on. So what is happening here? So this web page is cycling through a whole bunch of links, okay? So, and each time, so for the first link, it sets all of these links here to that particular URL. So there's a whole bunch of them, they've got a text shadow, and they take a time to draw. So this page sets the first link to the first URL, and then it times the next 5 frames, okay? So these times here, you can see in the first frame, it always takes quite a long time to draw. And then the second frame is actually pretty much 0 because it's trying to catch up, trying to keep that 60 frames per second. And then for the links that are visited, that third frame is quite a lot slower. So we can see that the first and third frames, where the repaints occur, and so that the purple links are the ones that actually are visited, and where the green ticks occur, that's where this page has detected that the repaints occurred. So it basically keeps cycling through them, but as you can see, it's pretty accurate, and we can play with the numbers here. So we can have a smaller text shadow, which will speed things up a bit, or we can use CSS transforms to make the whole thing, all those links, pretty much invisible. But again, it still works. We can still detect those repaints. So that's quite fun. So that works in Internet Explorer, and it works in Chrome. It works in Internet Explorer and Firefox. But Chrome is a little bit different. Chrome doesn't do asynchronous URL lookups, which is a bit of a problem. Basically, with Chrome, when you put a link on the screen, it will wait for the database lookup to come back before it paints the link on the screen. So the first time it paints the link, it will always be painted visited or not visited. So how can we do the same thing in Chrome? Well, a slightly different way of doing things is putting a link on the screen that we know isn't visited. And then we change the target of the link, the href, to a different URL. And if that new URL is visited, then Chrome will repaint the link. So here's what we do. We have a link that's not visited. We get a reference to the link. We change the href. And then we have to do a little trick here. So by default, Chrome won't actually restyle the link. If you just change the href, I found that if you kind of touch one of the style attributes, so in this case to set the color to something and then remove it, then Chrome will go, aha, I need to restyle this, and it will repaint the link only if the new URL is visited. So we have a slightly different technique for Chrome. So we have a whole bunch of link elements that we keep on the screen with a text shadow, and then for each URL we want to check, we update the link targets to that URL. We time the next frame with a requestAnimation frame. And if that frame was slow, then we know the link's visited. And it's quite a bit quicker in Chrome because because the lookup is not asynchronous, we only have to time one frame rather than the next few frames. So let's go have a look at that in Chrome. Okay. So this demo is slightly different. It actually self-calibrates. So it tries to find a value for text shadow and for the number of links. It tries to find a value which will give a nice timing difference. So in this case, it started off with a small text shadow and just a few links, and then it calibrated by, it kept going, increasing the numbers until it got, well, in this case, the visited links were about 70, 80 milliseconds. So as you can see, it's gone through a whole bunch of links again. Only had to time one frame for each link. And again, it's got all of those correct, I think. Yep, it's got all of those correct. And it's found out those links are visited. So the change in the URL also works in Firefox, which is quite nice. So yeah, just to summarize. So Firefox and Internet Explorer have the asynchronous lookups, and Firefox and Chrome will repaint a link after the href changes. So we have two techniques that work in 3 different browsers, which I think is pretty good. So how practical is this, you might be asking yourself? Well, yes, we need to do the calibration, but that works pretty well. To find out, if you've got a slower computer or a faster computer, we need to find the right value for text shadow. As I said, we can make the links invisible, so the user doesn't actually see this going on. How fast is it? Well, Chrome was the fastest out of those, and I could test about 16 URLs per second, which is okay, but it's a bit slow. So I thought, can I improve things a bit? So here's a slightly different technique I came up with for Internet Explorer. So rather than testing one URL at a time, I display 1,000 different URLs all in one go. So the 1,000 different URLs we want to test if the user visited them. And as we put them all on the screen, even if one of those links is repainted, we can detect that repaint happening, so it will be a slow frame. So we know that if the repaint occurs, then at least one of those links is visited. So we divide them in two, and then we display the first half on the screen and test for redraws, and then we display the second half on the screen and test for redraws, and we keep splitting them down until we get down to a single URL. And I'll show you this working in Internet Explorer. Yeah, it's working pretty nicely. Okay, so this time it's tested 1,000 URLs in 17 seconds, which is a lot quicker than we achieved with testing one at a time. Okay. So the study they did in 2010, they found these websites that were doing this for real. They were testing between 20 and 200 URLs. So the fact that we can test 1,000 URLs in 16 seconds, that's pretty good, and kind of measures up with what those sites were doing back then. So that's history sniffing. Thank you. So now we're going to go on to the really fun stuff, and that is how can we read pixels from the screen using a timing attack. So SVG is a scalable vector graphics. So it's basically you can have paths and lines and circles and stuff in an XML document, and this graphics format is supported by all browsers, even Internet Explorer. So where does HTML5 come into this? Well, okay, HTML5 basically says that you can embed and mix SVG and HTML elements in the same document. So yeah, SVG is not technically part of HTML5, but yeah, it kind of is. So yeah. Okay, so this is SVG. We've got nice, simple lines, paths, text, vector format. But the reason I'm looking at SVG is because of something called SVG filters, filter effects. So this lets us do nice, funky effects like this. So we can go from boring SVG to fun, fancy effects. So SVG Filter Effects is a separate spec to SVG, and it defines 16 basic operations, things like convolution matrices, blurs, displacement maps, change in colors and things like that. And you can combine these basic operations, you can kind of stack them up into a single filter to make the kind of fancy effects I just showed you. So you can do cool things like lighting effects, bump mapping, and so on. So SVG filters only affect the appearance of those paths on the screen. They don't actually change the paths, and it's not possible for JavaScript to actually kind of see what the SVG filter has done. So it's only a visual effect, really. So why am I looking at filter effects? Well, you can apply SVG filters to any HTML element in Chrome and in Firefox. And when I first found out you could do this, I thought, well, there's got to be something bad you can do with this, right? So I thought, okay, let's see if I can do a timing attack with SVG filters. So why would this work? Well, SVG filters are pretty complex algorithms, right? They're doing quite serious number crunching, and perhaps if we can find a certain filter that we can apply to a part of a web page, can we find a filter that takes longer for some input than other inputs? And if we could find, if we can find this filter, then perhaps we can do some timing attacks. So, we have input A and input B, and if we apply the same filter to it, it might take two different times. That's the theory, right? So I had a look at the Firefox source code, and I found this filter called FE morphology. So morphology is a fancy term. Basically, it is used to make lines thicker or thinner. And this filter takes a one parameter, radius, and that controls how much thinner or thicker the lines get. So there's kind of two modes. There's dilation, which makes things thicker, and there's erosion, which makes things thinner. So how does this work? How does this algorithm work? It's fairly simple. So the radius parameter defines the size of this box, that orange box you see there. And basically, it will pass this box over every single pixel of the input image. And each time it places the box, it will scan every single pixel inside that box to find the darkest or the lightest pixel, depending on if you're doing erosion or dilation. So in this case, it will find the lightest pixel, and it will set that pixel in the middle of the box to the color of the lightest pixel. And I've got a nice, fancy little animation here. Ooh. Okay, let's do that again. So basically, as it passes over, you can see that the line's getting thicker. Now basically, in the most basic case, if you just implemented this with no optimizations, you would have to do, for a particular size image, width times height, and particular size box, Rx times Ry, you multiply all those together, and that's how many comparisons you have to do. So this is potentially quite a slow thing to do, right? But in Firefox, there's this optimization to speed things up a bit. So this is the source code from the FE morphology filter a year or so ago in Firefox. And you don't need to understand the whole thing. But basically, here's the code on the screen at the moment is the basic, is the slow case, the non-optimized case. And in this case, you see those two for loops. Those are going through that entire box, Rx times Ry. And the inner loop is doing RGB and alpha. But you see there's three for loops there. But there's this optimized case. And in the optimized case, it only checks the right-hand column of pixels in that box. So it only has to do scan through RY pixels, basically. So instead of scanning the whole box, it just does one column. And that makes things a lot quicker. So when does this best case occur? Well, basically, if your image is completely flat, just a single color, then you will always hit that optimized case. And if your image is completely random and noisy, there's no flat areas, then you're always going to hit the worst case. So we have two inputs that we can give to this filter. So if we apply FE morphology to those two inputs, we get those two different outputs. You can see on the bottom right one, it's kind of gone all kind of blotchy. But basically, on the right-hand side, that will be a lot slower to apply this filter to. Okay, so how can we use this fact? How can we use this filter to do a timing attack? Because the thing is, what use is having a black and a noisy image? When's that actually going to occur, in the real world? But we can use more SVG filters to do something interesting. So rather than having a flat image and a noisy image, we can take a black area and a white area. And we can use an FE image filter, which is noise, and we can multiply those together. So if we multiply black with noise, we get black. And if we multiply white with noise, we get noise. Because in the top image, it's all zeros, so 0 times anything is 0, and the bottom image is white, it's 1, so 1 times anything is 1. So we go from black and white to black and noisy, which we can then apply FE morphology to, and that will be faster or slower. Okay, so now we have black and white. How can we actually do a timing attack with this? So how can we read pixels from an iframe? Okay, so here's what we do. We take our iframe, and using CSS, we crop it to a single pixel, the top left-hand pixel. And then again, we use CSS to blow it up to 100 times the size. So instead of a single pixel, we've got a nice large area. And then we apply our SVG filter, and we time how long that filter takes to apply using requestAnimation frame. And then we move to the next pixel, and we time that pixel, and we do that for the entire iframe. So going back to the black box again, you love black boxes, right? So in this case, the SVG filter is our black box. or the rendering, it's the whole page rendering, but it's the SVG filtering that we're interested in. So we can give pixels to it. We can give it black pixels or white pixels. And again, we've got the callback from requestAnimation frame. And we can time how long that filter takes to apply. And we can tell if we have black pixels or white pixels. So it's a little bit more complicated than that. So I'm not going to go into the details here. There's the white paper which goes into a bit more detail about this. But so when we're applying our filter, we're only interested in how long the filter takes to apply. We're not interested in anything else going on, any other rendering operations going on. So in Mozilla, there's this CSS attribute called moselements, and that's only found in Firefox. But basically, it lets you set the background of one element to be visually the same as another element. So let's just kind of take a snapshot of it. And the reason I do this is because if you apply an SVG filter to the original iframe, it'll have to redraw the whole iframe, everything in that, and that will kind of throw off our timings. So by applying it to a snapshot of the iframe, then we eliminate everything else except for the SVG filter. And the other problem we've got is, pixels in most websites aren't just black and white. You have grays, you've got colors, but we need black and white. So again, we can use SVG filters, come to the rescue, and we can apply a threshold filter to make things black or white. So let me just quickly show you how those SVG filters work for us. So we have a website here loaded in an iframe, and we can apply an SVG filter to it. So here's my threshold filter. It's kind of fun because the website's still working. It's still, you can interact with it and everything. And we can adjust our SVG filter threshold to get the right, to get the text that we want. The reason I've inverted it is because the black pixels are quicker to read than the white pixels, and because there's more black pixels, it will be quicker to read mostly black pixels and a few white pixels. Okay. So, so let's, you want to see the demo now, right? Okay. So, as you know, lots of sites prevent framing these days, right? So I had a look, kind of racked my brains trying to think of websites that still allow framing and have some interesting information on. So one of those is, if you go on a Google blog, they have this comments widget. There's Google Plus comments widget, which is in an iframe, and it's got your name on it. So I thought, that could be interesting to read. Let's hit this off. So, and also the Amazon website, you can frame that. So this is my orders page. So, we can read some interesting things. So, okay, so what's going on here? So in the top, we've got the original iframe. The second one down here is our enlarged version. So this is enlarged 8 times. And down the bottom here, we have got, this is our single pixel. So this box here is this top left-hand pixel blown up by 150 times. And as you can see, if it's black, the pixel's black, then our filter outputs nothing basically. And if it's a white pixel, we get our kind of colors there, our modified noise basically. Okay, so let's run this now and see what happens. So it does the calibration first to find out the times of the white and black pixels. And as we can see there, it's building up pixel by pixel, reading from the iframe and plotting the results onto a canvas. And again, all of this could be invisible to the user. So once it could build this picture up in memory and then send it back to a server. And in this case, it would have, thank you. So in this case, we've got my name, but it could be any kind of information that is on a website or a web page that we can frame. So that's pretty fun. I like that, but it's relatively slow. And also, we end up with a picture, and pictures are nice, but what would be really nice is text. So could we speed things up a bit? Could we make some assumptions about the text that is on the web page to come up with a kind of quicker algorithm? So what if we knew the font face and the font size that's going to be on the web page? And what if it was a fixed width font? So the space between the letters is equal. And what if we knew exactly where on the page our particular text is? So there's one thing which kind of matches all of those assumptions, and that is the source code of a web page. Now in Firefox, there's a kind of neat trick you can do. You can actually load the source page, the source code of a website into an iframe by sticking view-source in front of the URL, and it will show you the source of the page instead of the page. So there's all sorts of fun stuff that we can get at inside the source code of a web page. So obviously everything that's displayed on the page you can get at. But also there are things like cross-site request forgery tokens, authorization tokens, IDs, and things like that. So if we can get the source of a page, then we can get some interesting stuff. So I thought, instead of getting the picture of the text, how about we do a kind of OCR technique? We actually recognize the text and convert it from a picture into text. But instead of a kind of normal OCR algorithm where we study an entire image, because we're on a computer, the fonts are always the same every time, what if we could just read a few pixels from each character and figure out what character it is? So this kind of raises the question of, okay, which pixels do we have to read? If we read that pixel on the number 6, is that unique to 6? Are there other characters that share that pixel? How do we know? We have to have some knowledge of the font. So the idea is perhaps if we study the font really well, we get all the information about where each pixel is and each character, we can build up a kind of decision tree. So we can read one pixel, say some pixel somewhere that will be either black or white. And then if that pixel is, say it's black, then that kind of, we know that certain characters have that pixel set. And then we can test another pixel. And we know, that further restricts the characters that we might have. And we can keep doing that until we know which character to read. So the question is, how many pixels do we have to read? And is this, how straightforward is this to do in reality? So here's what I did. I decided rather than kind of doing this by hand, it'd be quite slow, it'd be quite boring. I wrote some JavaScript to do this on the fly. So what it does is the JavaScript takes a snapshot of the text we want to recognize. So in this case, instead of recognizing the whole alphabet, we're just going to look at hex characters. So the JavaScript will take these characters, it will draw them onto a canvas where it can manipulate the pixels and read the pixel values. And the first thing it does is apply the threshold. So the same threshold we apply to the iframe, we also apply to this text. So we have black and white. And next what happens is we take each of those characters and we draw them all on top of each other and build up this kind of heat map. So what's going on in this heat map is that the red pixels are the pixels used by exactly half of the characters. So the red pixels are used by 8 characters, but they're not used by the other half. And the orange pixels are ones that have a slightly different split, so they might be set by seven characters, or they might be used by 9 characters. But the red pixels are the ones we're interested in because they divide the character set in 2 essentially. So we take our heat map with all the characters, and we pick one of the red pixels, and we find out which characters use that pixel. So in this case, that pixel selected there is used by the characters 4, 7, A, B, C, D, E, F. And we take those 8 characters and we build up another heat map. And again, we find the red pixel, find which characters use that, and we keep building up this tree until we get down to the bottom. So by the time we get to our 4th pixel, we know in this case, if that pixel's set, we've got the character 7, and if it's not set, we've got the character F. And we build up the tree like this. So the JavaScript algorithm does this all automatically, and it spits out this data of this decision tree. So what we have is that instead of having to read the entire character, which is hundreds of pixels, we can just read select pixels for each character. So the orange pixels there, those are the pixels we need to read to recognize each character. So if we're reading hex, we only have to read 4 pixels. If we want to read kind of alphabetic lowercase and spaces, say, we only have to read 5 pixels. And if we wanted to read, most text, we could probably do it at 64 characters, or if we wanted to read base 64, we can just read 6 pixels. So this brings us to the final demo. So the setup is pretty much the same as previously, but in this case this is the source code of that Google Plus comments widget. And what's interesting about that particular widget is that your entire Google Plus profile is actually in the source code of that web page. So it's in the JavaScript. So even though it's just a web page for putting comments on blogs, every single piece of data, whether you marked it public or not, is in that source code. So it makes quite a nice target. So what we've got at the top here is this is the data that heat map algorithm spat out. So this is our kind of the raw data of our binary tree. So this is the number of pixels from if you kind of go along counting down rows. This is the first pixel we test, and then it jumps to a particular place in the tree. That's our data. So I'm going to press start, and fingers crossed this is going to work. So first of all, it's reading my Google ID. So from my Google ID, I can go to someone's Google Plus profile. So I can essentially de-anonymize them. And then there's a telephone number in the profile. I marked it as private, but it's in there anyway. And it's got my mobile phone number as well. There we go. So as you can see, that was a lot quicker than having to read the entire image, and we've got some nice actual values back as text. So in that case, I had to read. In the previous demo, you saw that it didn't get all the pixels right. In this case, because just reading a single pixel wrong will throw us off in the binary tree, it will get us a wrong result. It takes 3 readings for each pixel, and just takes the median, and that works pretty well in this case. So, which browsers does this work in? Well, in Firefox and in Chrome, you can apply SVG filters to HTML. I've only done this demo in Firefox. It's slightly easier because of that Moz element thing I told you about. I haven't yet had time to do a demo in Chrome, but I think it is possible. And the FE morphology filter, that also has a timing difference in Chrome. Unfortunately, Firefox is the only browser that lets us do the view source with the iframes. But of course, even without view source, you can still read the visual text on the web page. Internet Explorer is no fun really because it doesn't let you apply SVG filters to any old HTML. So this isn't possible in Internet Explorer unless they want to add that feature. Okay. So yeah, there's. I only looked at the FE morphology filter so far. I think there are probably other filters that have these timing differences. So I reported my original research I did in Firefox, and I reported this to Mozilla about a year ago, and they fixed that now in the latest version of Firefox. They fixed the FE morphology filter, but possibly the other filters that have the timing differences. But actually, these kind of bugs are really tricky to fix, and that's for several reasons. One is that browsers like to be really fast these days, and one way to fix these kind of attacks is to take out those optimizations. So Mozilla basically took out the optimization in FE morphology, which made the filter slower. Which is that's a trade-off, right? And also they actually had some fun fixing the code as well. So the first time they tried to fix the FE morphology, they took out that slow case, that entire block of code. They took it out, but actually there was still a timing difference. It was smaller, but because there were if statements right in the middle of the loop, they still made a tiny difference, and it was still possible to get a timing for the timing attack to work. So they took a few goes basically to get code that was would run in exactly the same time, no matter the input. And there are various things going on there, possibly compiler optimization. So even though you didn't specifically put in an if statement, the compiler still kind of optimized it and kind of made code that was slightly slower or quicker depending on the circumstances. So going back to the link redrawing, the history sniffing, well, one way to fix that is potentially to always redraw links, whether they're visited or not, when that result comes back from the history database. But again, that's a bit of a trade-off, right? Because if you redraw every single link on a web page, if you've got a big Wikipedia entry or some news page with lots and lots of links, that's going to slow things down. So the history sniffing attack, I found that more recently, a few months ago, and I've reported that to the browser vendors. They've not fixed it yet. I think they're still debating, what the best way to fix this is. And yeah, for the SVG filters, there's possibly other ways to prevent this. Maybe preventing, doing what IE does and not allowing SVG filters to apply to arbitrary HTML content. And if you're particularly worried about these kind of things, if you're on a website, well, you should be using X-frame options anyway, and that will prevent your website from being framed. Obviously, you should be doing that to prevent clickjacking anyway. And if you as a user are particularly concerned about this, well, with the history sniffing attack, you can clear your history regularly, or you can use private browsing for certain sites. But I think eventually these bugs do need to be fixed by the browser vendors. So that's it. Thank you very much.